Welcome friends, the fourth video of the formulation of the stiffness matrix of a CST. Now we have studied the many things. The first of all we have studied the psi function, that is the displacement function. Then we have studied the stress function. Then we have studied the relationship stress strain function. Then in a last one we have finding the pi p, that is the minimum potential energy function. So these all terms we have studied. Now these one are helpful us to formulate and assemblage the total matrix. Now here we have seen in a pi potential energy matrix we have considered the three types of the forces. So F matrix is equal to my my volume of, means this is the weight matrix, this is my weight matrix. Then this one is the point matrix, this is the point matrix or the point load, and this one is the surface traction load. So all these loads I have considered as a f of this one. So F matrix is equal to triple integration of matrix. F matrix is equal to triple integration of shape function transpose into x x matrix plus p matrix plus double integration, that is the surface traction matrix, it is into ns shape function multiplied by traction force. So this one, so this is the f. So put this f value into a pi p. So pi p is equal to 1/2 d transpose multiplied by triple integration of a strain energy. This is the derivation of the strain energy. So strain energy B transpose into the D matrix into B matrix dV into D matrix minus D matrix का transpose, this one is the transpose multiplied by F. Now F is equal to this value, F is equal to this value, this value. So just instead of putting all this value and making the calculations very complex, I am writing here that is the F. So writing here the F. So by taking a partial derivative of the both the displacement, that is the partial derivative of the pi p with respect to d with respect to d. Now here that d is also available, and here d transpose come out, so that partial derivative of this one, if once we have derived, then we are getting that is equal to this term, that is equal to this term multiplied by this minus this is equal to 0, because we want to use the minimum potential energy. So just to keep this potential energy minimum, so partial derivative equal to 0. Hence by putting these values, hence this one is equal to this term comes here. Now here this one is the minus f, this one is the minus f. So here this is equal to 0, this comes to here, hence this value becomes this one. So my equation becomes strain energy is equal to force energy or the force parameter. So this is my strain energy, this is my force energy. Hence my K matrix, that is the element stiffness matrix, is equal to triple integration of this one. Triple integration of this one means this is only the value. This is only the value. Hence for the constant thickness, this thickness is very less. I can keep it that T is equal to T is outside. So instead of triple integration, I would go for the double integration. Double integration of beta matrix multiplied by constitute D matrix into beta matrix along x and y parameter, So this is my K matrix. So this is my element stiffness matrix for my triangular part. So if this is my triangular element, if this is I, this is J, this is M, then this is my element stiffness matrix, that is the beta matrix multiplied by D matrix multiplied by beta matrix. But here instead of beta matrix, I would say this is not the beta matrix, this is the beta transpose matrix, and this is the beta matrix. So this way I am very easily calculating a K matrix. Here I use the word K very easily, but you know this one is not very easy. We are first of all finding the shape function, that is displacement function, then the stress function, then the pi p, and and later on, just by manipulation into this video we are reaching to a K matrix, that is the stiffness. So this is my stiffness matrix. So this is my stiffness matrix. Now this stiffness matrix I can write for all the nodes. I can write for all the nodes, for I node, J node and M node. So this my K matrix is equal to matrix of matrix Ki, Kij, Kim, Kii, Kji, Kjj, Kjm, Kmi, Kmj, Kmm. So this is my final element stiffness matrix. So that this is my Kii, this is Kij, Kim, Kii is equal to beta matrix transpose beta I transpose into D matrix into beta I matrix. Now see, both are the I. Now here the Kij. So here the term is I and here the term is J. Here Km. So here the beta matrix I and beta matrix M. So keep in constant watch that how to write this beta matrix multiplied by T and A. So this one is the simplification of this one. So finally I am writing my force matrix F1 F2, my force matrix is equal to K matrix into my displacement matrix, and the summation of all this k. So my force is equal to K multiplied by delta matrix. So K is equal to 0 to n K, all the elements I need to consider and assemble that one because this is only for three nodes. This matrix, stiffness matrix we have developed only for three elements. We have developed only for three elements. If this is I, J and F, but this element there are the more number of the elements, that's why we have assembled that one. So this is the formula for assembling. So K matrix is the assemble of this 1 to n of all the elements. So I am getting the force matrix is equal to K matrix into D matrix, and then we need to solve it. So this is the assemblage of this one. But sometimes my local axis CST are not parallel to the global axis. So when my CST axis means this is the diagram. This is the diagram. If this one is not match up with my global axis X, if it has a certain angle, let us take this one is the angle. So instead of this x-axis, it has a some angle this one. Then we need to introduce the transpose matrix. And this is the value of a transpose matrix. This is the value of the transpose matrix. So that your K matrix, K matrix is equal to transpose matrix multiplied by all other values. So generally this is not asking in the examination, but you need to keep in your mind, that is whenever such angle is occurs, so that when this is not related with the x-axis, if my this axis this sorry if my edge or this axis along x local axis is not with a global axis, then I need to use the trans transform matrix, or yeah, transformation matrix. So I need to transform this one. So this is the transformation matrix. This transformation matrix to be multiplied. So K is equal to my transformation matrix multiplied by my beta matrix. So this way we can define our element stiffness matrix for the CST. Generally, in examination they will ask any type of the derivation on this one. So keep the uh, keep study on this one, and try to derive this one. Thank you to all.